Welcome to session 4. My name is Arnold and I will be your instructor. In this session, we will talk about defining your network within AutoCAD. In the prediction pipeline, we define the model in the last stage, which is called train. You often have to use sensible defaults, which we discussed in session 1, but you often have to tweak your networks in response to what you see on your loss graphs. The prediction pipeline in AutoCAD has a few stages. In the first stage, we prepare the data using prep.m, and this gives us our raw data files, train and test CSV. These data files are then windowed using pre.m, and the windowed files are sent to your network for training. Two files define the network, network.m and config.m. And finally, your network is run on a prediction of some kind. The prediction pipeline itself is orchestrated by main.m. The network definition is contained in network.m, and this is the file that we will look at in this session. Here's an example of a simple network.m. It consists of 4 sections. The network section defines the network itself. The train section defines how the network will be both trained and tested. Deploy is used when you want to test out your network on some novel data. And finally, the solver section contains all the configurations for the solver you're using. The word called network defines your network. In this case, we see a simple 2-layer feed-forward network followed by a single linear combiner. We find your train and test setup in the train section. We define the deployment setup, which is for novel data, in the deploy section. This is used in predict. And finally, the solver settings are simply for you to override the defaults put in place. If you click on debug, then the solver settings that you have used will show up in solver.prototext as a separate file. Let's see how this works in practice. This is a 2-layer network with a linear combiner. This corresponds to the definition shown below. Notice that the definition contains a name called NN size. This name is contained in config.m. If we set NN size as 5, then the first layer has got a size of 5 because it would be 5 perceptron. And the second layer would be 2 because 5 divided by 2 is 2 with integer division. And that's layer 2. Finally, we have the linear combiner, which is simply a single output, and the linear combiner, it's called an inner product. The 1 corresponds to the fact that there is just one output for this combiner. So again, layer 1, followed by layer 2, followed by the combiner. And that defines our network. We need a name called temps, which is a unique name for the weights of this network to be saved. You can easily define your own neurons or your own layers. This code shows you how to use a ReLU output with an inner product. And you use it by specifying how many neurons you want to use for the layer. So 32 perceptron simply means 32 perceptron units arranged in a single layer. You could say a linear neuron is simply the inner product alone by itself without the saturator. Each inner product is a single layer of linear neurons. So 32 inner product, for example, means 32 linear neurons in a single layer. And you just apply a saturator to the entire layer. So 32 inner product 10H, for example, would mean a hyperbolic tangent saturator over 32 linear neurons, which simply is 32 regular perceptrons. There are a few saturators you can use. I've mentioned ReLU. It's very fast, and you should try this first. You can also try leaky ReLU, or of course the hyperbolic tangent. We will use tangent H in more advanced applications. Data normalization is all about changing the size of your inputs so that they work best with your neural networks. Again, this is done in the prep stage. We will only discuss normalization for prep. You always want to fix the normalization right at the start and not change it at all if you can help it. So what is normalization? The first thing is making sure that all the inputs are about the same size. And second, to ensure that the inputs have a magnitude of about 1. Normalization is crucial for neural networks, but it's not so important for other ML techniques like decision trees or SVMs. Let's examine the effect of uneven input sizes. Let's say we have an input vector. Let's suppose it has 3 elements, x1, x2, and x3. If you look at the average values of these inputs, you'd notice straight away that x2 has got about 10 times a larger magnitude compared to x1 and x3. What is the effect of this? Well, if the weights are about the same size, and let's assume for the moment that B, the bias, is 0, taking the inner product simply means that x2 will dominate the inner product. So in other words, large inputs dominate learning. This is okay if the inputs are relevant, but if they are not important, the neural network will have to work harder to ignore them by reducing the size of the weights. This takes extra learning iterations and is not at all guaranteed to occur. Therefore, it is crucial that you make all inputs about the same size on average. And it's not easy to do this because you could always lose crucial detail by normalizing. To go further, you need to understand a couple of facts about the backpropagation algorithm we use to train our neural networks. You already know it is the algorithm we use to calculate changes in the weights along with gradient descent. Now, the key fact is that the changes to the neuron's weights is proportional to the slope of the saturator you use when that neuron is active. The horizontal axis is the input into the saturator. In this case, we have a hyperbolic tangent saturator. And the vertical axis is simply the hyperbolic tangent value of the inner product. Then the ends of the saturator have a very small slope, and therefore, because the learning is proportional to the slope of the saturator, a small slope simply means that very little learning occurs. On the other hand, if the values of the inner product fall within the central part of the tangent h, then because the slope is much larger, most of the learning will occur here. Let's look at this again. So let's say we have the input vector with 3 elements. And let's suppose the elements all have large sizes, well above 1. And we assume that the weights are on the order of 0.1. Clearly, the inner product will be very much larger than 1, simply because the x's are very large. Because the inner product is larger than 1, the region of the tangent h which is activated would be on the extremes where the slope is small, and therefore learning is slow. What this means is that when you have large input values, learning becomes very slow, and the most of the cycles would be spent trying to reduce the values of W1, W2, and W3 instead of actually learning. A symptom of this is that your network will not learn. So it is crucial to make sure that your inputs have a magnitude of about 1. I would say you could get away with values below 10. So a symptom is that your model doesn't train well. Always check the input sizes as a first resort. Having understood the need for normalization, let's look at a few techniques and how you can do this. Well, the obvious way is to simply subtract by the mean or the median and divide by the standard deviation. This is a simple way of doing things. But you need to be careful to fix the mean or median value that you use for your normalization process to make sure that the same normalization is used for both training and testing datasets. And you want that normalization also to be used when you predict on novel values. A second method is to use a one-to-one transformation, which can shrink values like a log. Be careful using this because the log could overshrink the signal and you lose the fine details of the signal itself, which are valuable for prediction. In many industrial applications, you can use difference networks, which we will discuss next. Again, I want to emphasize that you have to use the exact same normalization for both training and testing, and also when you deploy. Otherwise, your network will not give the right results. I'd encourage you to discuss this aspect in your groups. I have a question next for you. You're quite familiar now with the inputs that need to be normalized, but what about the outputs? Do they need to be normalized as well? Yes, they do. Suppose Joe normalizes his training data set using a training mean in SD, and then does the same for his test data set, but using the test mean in SD. What can you really say about Joe's work? Good or not? Next, should we normalize the actuals, the Y's, not just the inputs? I'd like you to give this some thought, and we can discuss this in the forum. Normalization occurs in the prep stage, which is controlled by prep.m. This is a simple prep.m which normalizes based on the mean and SD. Run is the main function, and it calls the normalization. In this case, the normalization is simply y minus the mean, which is 25, and divided by the SD, which is 5. The map applies this to all rows of column A. I'd like next to discuss difference networks. This is a simple change to your network which can dramatically improve the forecasting capabilities of your model. You should be quite familiar with the naive network where the inputs are fed directly into the model for a prediction and then compared against the actual outputs. The problem with this network is that we are essentially throwing away the most recent value, y naught, which is known. The t plus 0 or the present values are very important for shorter lead times. And naive networks are unlikely to be persistent except for toy problems. The difference network separates out the y naught value and uses it outside the network. Here's how it's done. We additionally have a y naught value, and what we do is we add the model output to y naught as our predicted value. This simple change can dramatically change the predictive power of your network. Let's see why this works. What's happening is that your model no longer has to learn y, it has to learn instead y minus y naught. There are many advantages to doing this. The first is that there are many more examples of y minus y naught than just the y value alone, and this is especially so if the actuals are spiky. More examples, of course, lead to better training and can be very helpful for rare events. Secondly, even if the predictions were bad, or on average 0, the risk and lag would be very similar to persistence. So in practice, difference networks often start with a lag and test loss equal to that of persistence. Next, y minus y naught is likely a much smaller value than y, so there is less need to run a normalization. Of course, you should go ahead and try and normalize the y values anyway. Here's how you implement a difference network. The first section in your train loads up the train dataset, while the second section loads up the test dataset. The difference network is defined below these two. What you see here is that the output of network is added to the y naught value, and this is compared to the y actuals with a Euclidean loss. The Euclidean loss is synonymous with the RMSE. If you look closely at the first data loading section, you'd see it has 3 lines. The column 1 is simply the y, which we set by convention. This comes from train preprocess.csv. Column 2 is y naught by convention again. And the remaining columns from 3 all the way to the input size are your input vector x, and this could be windowed data or the feature engineered data. The code on the left shows a difference network where the network is added to y naught before being compared to y. And on the right, we have the naive network where the network is directly compared to Y. Let's say Joe has a network. Joe's network does not explicitly show Y0. Instead, what Joe has done is to fold in Y0 as one of the inputs in his input vector X. Let's assume everything is normalized. The question, is this equivalent to a difference network? And the second is this a good solution? Now, both questions need some thought, and I'd like you to discuss them in your groups. In this section, I'd like us to talk about 3 very important techniques to help your network learn well. All 3 techniques deal with overcoming the problem of overfitting or overtraining, which is very common with neural networks, as we discussed in session 3. The problem of overfitting is that bigger models tend to memorize the training data. The symptom is that the test losses remain high while the training losses go down to nearly 0. But bigger models are needed in order to learn more complex data. The 3 tricks we use to prevent overfitting are early stopping, dropouts, and regularization. I talked about early stopping in session 1. If you recall, early stopping simply means stopping training if the test losses start to increase. This process is controlled by 2 parameters, the skip and the length. Let's say we have a loss curve, and these are test losses. The horizontal axis represents the iteration number, and the vertical axis the test loss. If we mark in circles points in which early stopping samples this curve, because there are 3 points between samples, we say the skip is 3. Skips help us to overcome the problem of noise. Finally, because we have 4 of these values to use, we say that the length is 4. Skip helps to reduce the influence of transient changes in the risk, and length helps us ensure that sufficient samples are obtained before the decision to early stop is made. Early stopping is always enabled for AutoCAF. If you look at the solver section of network.m, you can add an early stop section. In this case, the length is 25, and that's the first argument, and the skip is 20. These defaults are good for batch learning, and you shouldn't change them too much unless you change the batch size, for example, when you use stochastic learning. Probably the most important technique you would need to use, apart from early stopping, is dropouts. So what is dropouts? Well, it has 2 effects depending on whether you're training or testing. During training, a dropout layer will temporarily and randomly disable neurons in the layer below it during training. The percentage of neurons selected for disabling is called the dropout probability. The weights of the disabled neurons are not changed, but only for that iteration. In subsequent iterations, if that neuron is not disabled, its weights are changed as normal. This can really help you prevent overfitting, as you will see in the next session. During testing, all the neurons are turned on, and this is true also for deployment. The dropout layer has got no effect. Let's say we have a feed-forward network, and we want to add dropouts to layer 1 and layer 2. All we need to do is to add a dropout D1 and D2 after layer 1 and after layer 2. This is how we do it in code. If you notice, what we have done here is to just insert D1 and D2 after layer 1 and layer 2. The 0.1 indicates a dropout probability of 10%. In general, we don't want to use dropout probabilities which are too large. As a rule of thumb, you should be cautious about using a probability of above 0.3. If your dropout probabilities are too large, your network will not train. But if your probabilities are too small, then the dropout layer has no effect, especially for smaller layers. I would also recommend not hard coding your dropout probability like how we have done in the previous example. Instead, use the config. You can always redefine the standard perceptron or create a custom one. For example, Here I've redefined the perceptron with a config called dropout prob. This means that all subsequently defined perceptrons have a dropout layer attached to them. And here's an example of a custom perceptron where we add the dropout layer. This custom perceptron uses a leaky ReLU with a leak of 0.05. Finally, I'd like to discuss regularization, which is simply adding a factor to your risk. L1 regularization adds the sum of the absolute values of all the weights in your network. L2 adds the squares of the weights of your entire network. And this is the default. The numbers lambda 1 and lambda 2 are called the weight decay, and they should typically range from 10 to the minus 6 to 10 to the minus 4. If your weight decay is too big, then this term will dominate the risk minimization process, and you will not get a good learning result. On the other hand, if the weight decay is too small, this term will not help. Regularization is defined also in the solver section of network.m. If you want to change the type, you use the option regularization underscore type, and you can set it to L1 or L2. By default, we use L2. The weight decay is the other option. In this case, I've set it to 10 to the power minus 4. I'd advise you to stick with L2 by default, especially when you start out. And of course, you need to use a weight decay of 10 to the power minus 6 to 10 to the power minus 4. Start with smaller weights and progressively increase them. Bear in mind that the losses you receive now will be an addition of the true risk with the extra regularization term. That's all for session 4. I'd like you to go back to your lab 1 and improve your prediction for SG temps using early stopping, dropouts, and regularization. Good luck.